Welcome to MarkScheme. Graphs and key features. Everything you need made visual. Give a mathematician a curve, and they don't just see a wiggly line. They read it like a story. And the plot points of that story are its key features. Where it crosses the axis, where it turns, where it's symmetric, where it flees off to infinity. Master those few features, and you can sketch almost anything. Describe it in words, or reconstruct it from a written clue. In this video, we'll name every key feature the syllabus asks for. Then turn your graphics calculator into a machine that hands them to you and finds where two curves meet. Here's exactly what we're covering, straight from your syllabus. Two subtopics at once, because they belong together. 2.3. Creating a sketch from information or context, including copying a graph off your GDC screen onto paper, and using technology to graph functions, even sums and differences of them. And 2.4. All the key features, maxima and minima, intercepts, symmetry, vertices, and horizontal and vertical asymptotes, plus finding where graphs intersect using technology. If you haven't met functions and domain and range yet, that's 2.2. Watch that first. First, a distinction that quietly loses marks. A sketch is not the same as an accurate plot. On the left is an accurate plot. Every point measured, to scale, on graph paper. That's slow. And the exam almost never wants it. On the right is a sketch. No fussy grid, no measured points, just the correct overall shape, drawn smoothly, with the key features marked and labeled. The intercepts, the turning point, the coordinates that matter. A good sketch must show the right shape, the intercepts, any turning points, any asymptotes, and clear labels. Shape plus features. That is what earns the method marks. So here's the heart of the topic. A tour of every landmark on one curve. This is an even function, symmetric, and it's rich enough to show off almost everything. What each feature light up in turn. First, the x-intercepts, where the curve crosses the horizontal axis. At those points, y is 0. So these are the roots, or zeros, of the function. This curve has 4 of them. Next, the y-intercept, where the curve crosses the vertical axis. You get it by setting x equal to 0 and reading off the height. There is always exactly 1, because the function gives one output for that single input. Now the turning points, where the curve changes direction. This top point is a local maximum, a peak. Here it also happens to be the y-intercept. And down in the two valleys are local minima. Maxima and minima together are the key turning points. On a parabola, there's just one, called the vertex, and the symmetry. Fold this curve along the vertical line, x equals 0, and the two halves match exactly. That line is its axis of symmetry. Spotting symmetry halves your work. Whatever happens on the right is mirrored on the left. Polynomials never run off to infinity in a wall-like way, but many other functions do. And that brings in the last two features. Asymptotes. An asymptote is a straight line. The curve gets closer and closer to, forever, without ever touching it. Here's a curve with one of each kind. This dashed vertical line, x equals 1, is a vertical asymptote. As x creeps toward 1, the curve shoots up on one side and plunges down on the other, hugging the line but never crossing it. Vertical asymptotes appear where a function would divide by 0, and this dashed horizontal line, y equals 2, is a horizontal asymptote. Far out to the left and far out to the right, the curve flattens toward that height. It describes the long-run behavior. Notice, the curve approaches the line, but the sketch must never be drawn, crossing it near the ends. One last feature bridges both subtopics, where two graphs cross. Draw a parabola, y equals x squared, and a straight line, y equals x plus 2. The points where they meet are the intersections, the solutions of the two equations at once. Here they cross in two places, one dot up here, one down there. Your calculator finds these in seconds with its intersect tool, and will do exactly that by hand and on the GDC a little later. For now, just see it. Two curves, two crossing points, each marked with a green dot. A huge chunk of paper 2 is graph this on your GDC, then reproduce it on paper. The screen gives you the picture, but marks come from what you label. So here's the reliable routine. Step 1. Note the window, the x and y minimum and maximum on the screen, so your paper axes cover the same range. Step 2. Draw axes with a sensible scale to match. Step 3. The marks. Step. Plot and clearly label every key feature you found. Intercepts, turning points, asymptotes with their coordinates. And step 4. Join them with one smooth curve, not a jagged dot to dot. The examiner is grading your labels far more than your artistry. Your syllabus asks you to graph not just functions, but their sums and differences. And technology makes this painless. The idea is simple and worth picturing. To graph f plus g, you add the two heights at every x value. Take f of x equals x, a line, and g of x equals 0.4 x squared. A parabola, at any x, stack one height on top of the other. Here at x equals 2, the line gives a height of 2, and the parabola gives 1.6. Stack them, and the sum sits at 3.6. Do that at every x, and you trace out the sum curve in green. On the GDC, you just type y3 equals y1 plus y2. No algebra needed. And for a difference, subtract instead. Then read its key features as usual. Finding intersections shows up on both papers, so know both roots. On paper 1, with no calculator, you set the two functions equal to each other. Solve that equation for x, then substitute back to get y. Each intersection is one x and one y, a coordinate pair. On paper 2, let the GDC do it. Enter the two functions as y1 and y2. Graph them. Choose a window that shows every crossing, and use the intersect tool. It drops a cursor exactly on the meeting point and prints the coordinates. The one warning? It finds one intersection at a time. So if the curves cross more than once, run it again for each point. Miss a window, and you'll miss a solution. Time for a ladder of examples. Easy to hard, all my own. Example 1. Read every key feature of this parabola. F of x equals x squared minus 2x minus 3. Let's pull them off one by one. The x-intercepts. It factors as x minus 3 times x plus 1. So it's 0 at x equals 3, and x equals minus 1. The points -1, 0, and 3, 0. The y-intercept. Set x to 0, and you read -3, straight off the constant. The point 0, -3. The turning point. Here, minimum, the vertex. By symmetry, it sits halfway between the roots, at x equals 1. The height there is 1 minus 2 minus 3, which is -4. So the vertex is 1. -4. The axis of symmetry is the vertical line x equals 1. And the minimum value of the function is -4. Every feature labeled full marks. Example 2. The same skills. But now, the numbers are ugly. So the GDC earns its place. Find the x-intercepts, and the vertex of f of x equals x squared, -3, x minus 5. These roots aren't whole numbers, so factoring won't help. Graph it instead. Type it in as y1 and hit graph. Pick a window wide enough to see both roots and the bottom of the curve. X from -4 to 6. Y from -8 to 4. Now use the 0 tool twice. It reports x equals -1.19 and x equals 4.19. Then the minimum tool lands on the vertex. 1.5 minus 7.25. Write each value down to 3 significant figures. That's the paper 2 accuracy rule. And you're done. No algebra, 4 clean features. Example 3. Ties it together. The intersection we teased earlier. Where do equals x squared and y equals x plus 2 meet? By hand. Set them equal. X squared equals x plus 2. Bring everything to one side. X squared minus x minus 2 equals 0. That factorizes neatly into x minus 2 times x plus 1. So x is 2, or x is -1. Now substitute each back into the easy equation, y equals x plus 2, to get the heights. X equals 2 gives y equals 4, and x equals -1 gives y equals 1. So the curves cross at the points 2, 4, and -1, 1. Exactly the 2 green dots. On paper 2, you'd skip the algebra. Graph both. Run the intersect tool once for each crossing. And read the same 2 coordinate pairs off the screen. Same answer. 2 honest roots. Example 4. Steps up to a curve with asymptotes. A light taste of the rational functions coming later. Sketch g of x equals 1 plus 3 over x minus 2. Attack the features in order before drawing a single line. Vertical asymptote first. The denominator, x minus 2, is 0 when x equals 2. You can never divide by 0, so x equals 2 is a vertical wall. Horizontal asymptote. For huge x, 3 over x minus 2 shrinks to nothing. So g settles toward 1. The line y equals 1. Draw both as dashed guidelines. Now the intercepts. Set g to 0. 1 plus 3 over x minus 2 equals 0 gives x minus 2 equals -3. So x equals -1. The point -1, 0. And set x to 0. 1 plus 3 over -2 is 1 minus 1.5, which is -0.5. The point 0 minus 0.5. With the walls and the crossings pinned down, the shape is forced. 2 smooth branches, each hugging both dashed lines, but never touching them. Notice the curve approaches the asymptotes and stops. It does not cross them. 4 features. 1 clean sketch. Before the exam craft, 3 edge cases that separate a clean sketch from a sloppy one. First, and it's worth repeating, an asymptote is approached but never touched. The single most common sketch error is letting the curve slice through its own asymptote. Draw it hugging the line and stopping. Second, pick a sensible GDC window. If it's too tight, a root or a turning point can hide just off the edge of the screen, and you'll swear it isn't there. Always zoom out to check the big picture, then zoom back in. Third, use symmetry to save time. An even function, where f of minus x equals f of x, mirrors in the y-axis. An odd function, where f of minus x equals minus f of x, has half-turn symmetry about the origin. Either way, you only have to work out one side. Now, the exam graph, other channels gloss over. Your graphics calculator has 3 heroes. You must know cold. The graph screen itself, the table of values, brilliant for checking a specific point or spotting where a sign changes, and the analysis menu, which hands you zeros, minima, and maxima, and intersections. 3 more that bank marks. Choose a window that shows every intercept, turning point, and asymptote before you copy anything down. Features off-screen are marks gone. Label every feature with its coordinates, because that is precisely where the method marks live. An unlabeled curve scores almost nothing. And remember what a sketch is. The correct shape with its key features, drawn in one smooth stroke, not a painstaking plotted grid. Draw fast. Label everything. Finally, the 4 traps that quietly cost marks. 1. Missing a key feature. An unmarked root or turning point you didn't label. If it's a feature, mark it. 2. Drawing the curve crossing its own asymptote. The curve only approaches that line. It never touches it near the ends. 3. Confusing a sketch with an accurate plot. Either wasting minutes plotting a careful grid or drawing a quick sketch, but forgetting the labels that actually earn the marks. And 4. Trusting a bad calculator window that hides a root or a turning point off the edge. Always zoom out to check nothing is missing before you commit. Sidestep these 4, and graphs become some of the easiest marks on the paper. And that is SL 2.3 and 2.4, fully covered. How to read every key feature off a graph. How to turn your GDC screen into a labeled sketch on paper. Graphing sums and differences. And finding intersections with technology. Next in the course, we chain functions together and then run them in reverse. Composite and inverse functions. For more, that's markscheme.app. See you there.